Basically, specific heat or heat capacity, you've seen these terms in what do you call the thermodynamics. So thermodynamics, of course, is a black box study. You input something and you get something out. You don't know anything about what is going on inside. But that's quite amazing. Without really knowing what's going on inside, classical thermodynamics allows you to get the answer for what you put in. So that's the beauty of that study field. Specific heat, I will specifically talk about electronic specific heat. Because after all, metal is full of electrons, so most of the properties, especially the specific heat, is determined by electron specific heat. You also saw that the color is also determined by the electrons, color of the metal. So here, this is electron specific heat is C sub E, and that is defined as a D of total kinetic energy of electrons divided by the, for example, temperature. So basically, it is defined as how much the kinetic energy of an electron changes depending on the temperature. And you can see immediately, you can guess immediately now that must depend on what? Density of states, right? Density of states mean that because, you have electrons and you raise temperature, so you change the Fermi distribution. How far up electron can go depends on density of states, right? So really, this property is connected strongly to the density of states. And for the time being, I said this is d sigma dt. Okay? And here, total kinetic energy is given by integral between 0 and infinity, GE, FE, E, dE. Does it make sense to you? Concentration was exactly the same equation without E, right? Concentration, we always had this N, E, something like this. Now, in order to find the total kinetic energy, you have to multiply this. So if you take this as if this is a bar graph, right? Specific energy times this plus specific energy times this plus specific energy times this just gives you the total energy. That's why you're multiplying with energy. Okay? So this is a way to get total energy. And because we have density of states here, we have to we always draw something like this. Okay, whenever we see density of states for 3 dimension, we get something like this. Right. E to the 1/2 relation. And up to a certain level, there's a Fermi level. Fermi level. And here we assume that thermal energy kT is much smaller than average kinetic average energy of electrons, approximately given by how do I get this? Let me just show you. Average energy is given by 0 to EF. For 0 Kelvin, GE E, okay, divided by we are assuming 0 Kelvin. This is for T equals 0 K. That means we don't have Fermi Dirac function anymore. So this is simply concentration of electron, total number of concentration on a denominator, and a numerator you have this total energy. Okay? And this is now, so we have this, but we just assume that I guess the main point is that we assume that this condition holds. And if this condition holds, then that means we only need to consider only around Fermi level. There is a region right? Because this is small, and we just need to see how much the total kinetic, how much total energy changes when we have change in temperature corresponding to this small region. Okay? That's the idea. So we are going to consider only on the region EF minus KBT larger than E, larger than EF plus KBT. After all, electrons here are all stuck and they don't change. What changes the energy is only on this region. Okay? So now I'm going to introduce, I have introduced one sort of assumption. I also introduced other assumption which says in this region, GE is constant. What does it mean? Only in this region, GE is like this. GE doesn't change. Same. So here, this is like a new GE, density of states. That's okay. I mean, this is almost straight. This is almost straight now. Okay? After all, maybe we are, of course, here on this side, we are underestimating GE. But here we are overestimating GE. After all, it's averages out and it's about the same. Okay? So we use same G. So G is constant. For this region only, right? We also assume that, it's not the assumption, but by definition, Fermi-Dirac function at the Fermi level is 1/2. That's by definition. So let's see how much more energy we get. After all, we change temperature, so we get more electron excitation, and we want to see how much energy how much increase in energy the total electron system gets. So within so number of electrons that get, for example, thermal energy. How many electrons get more thermal energy is a question here. And then that is same as G at EF. It's a constant. G is constant. So let's just say it's G EF times FE times E. Right? Probability of finding electron, G is the density of states, and times energy. That's basically the number of electrons. Okay? And that is given by G EF. This is 1/2 times 1/2 times 2. Energy range we're talking about is here. So that's 2 kBT. Okay? Constant times 1/2 times 2 kBT. So and sigma is this number times this. Each electron gets this much energy, extra energy by temperature. And this many electrons, this number of electrons gets this energy. So after all, we get 2/3 kBT times GEF times 1/2 times 2 And this is now 3/2 G EF K sub B square T square. So once we have that, we have, now we can calculate CE, electron specific heat. Electron specific heat is 1/3, electron specific heat I have to write down. It's a d sigma dt. So we just have to differentiate this with T. So 2 goes up and just T remains. So that's 3 So we did lots of approximations. Probably the most drastic one is this one. I said Fermi function is 1/2 here. Not only this point, but it's around here. It's 1/2. That sounds pretty drastic, but it's a good approximation because this is what we get. If you do the rigorous calculation yields, rigorous calculation yields something like CE equals to 1/3 pi square K Here's what rigorous equation yields. It's pretty close, isn't it? This is 1/3, but this is pi square. So if pi is 3, we get exactly the same equation, right? And usually this part is called gamma. So CE is always given as gamma tau. By the way, I said CE because there's also CP, which is proportional to T to the third. P is for phonon. So there's also a contribution from, little contribution from phonon. Phonon means lattice vibration. So you raise temperature, you excite more phonons, so that total energy of the system increase. Okay? So usually you get contribution from both. And because of this two term, what you get is C equals to CE plus CP is gamma T plus alpha T. So people usually very often write C over T equals to gamma plus alpha T squared. Okay? And here gamma is 3 kb square G EF, which is 2 point, well, doesn't, it's okay. So what people measure is the following. One, people measure something, specific heat. People measure specific heat and plot C over T on a vertical axis, and horizontal axis is T to the square. Then measurement results usually get something straight. And you extrapolate this like this. That's a measurement. And here, slope is alpha, and intersect here provides gamma, right? So what I'm trying to say is that by measuring specific heat as a function of the temperature, one can get gamma, and with gamma, you can get density of states for Fermi level. Remember, if you get gamma, and this is just constant, so this is, in other words, this is a measurement of the density of states at for the Fermi level. Thermal conductivity. Okay? And then we have a bar. And thermal conductivity, you know, it goes from high temperature to low temperature. And then there's a furnace roll. How do you pronounce this? It's French, right? Free. Okay, it's French. J equals minus kappa d t dx. So I'm just talking about one-dimensional case. And kappa, thermal conductivity, is given by 1/3 CE. Now I know why. Now you know why. I cover the specific heat first. And then velocity, average velocity times L. So here's this L is mean free path, approximately given by average V tau. So this J, of course, is a current, thermal current, and kappa is basically the some proportionality constant, and dt dx is the temperature gradient. Temperature gradient, how temperature changes as a function of the unit length, for example. Now, kappa. is given by specific heat. That means larger the electron can change its energy for a given temperature, then, you know, basically it can carry more energy, right? It can carry more energy. Velocity, of course, it is electrons that are moving. So faster the electron can move, faster the heat is also transferred. By the way, but after all, the electrons are carrying the heat energy. Okay? And L is a mean free path. Mean free path means electrons are moving, electrons moves, and then hits something and stop, and then moves again and hits something and stop. So that is given by velocity times relaxation time, right? Okay. So the longer the relaxation time, or lesser, smaller the scattering, you get more higher thermal conductivity. So everything makes sense, I think, I hope, to you. Okay? And as we learned, specific heat is given by 1/3 pi square kB square GEF tau T. And also, if you flip back, you get this density of states at Fermi level is 3/2 N divided by EF. This we covered previously. Okay, so we get all these information. So we throw this into here. So we put into here and then put this into here. So basically, let me write this again. CE now becomes 1/3 pi square kB square 3/2 N EF tau. And also average we replace by Fermi velocity. Remember, Fermi velocity is given by, you know, Fermi energy gives Fermi velocity. And L here is Fermi velocity times tau. So we put those relation into here we get kappa equals to 1/3 pi square (3/2) NEF T so we get so at the end we get this result that kappa is proportional to T. Everything is proportional to temperature. If you measure kappa as a function of the temperature, This is what you typically get. At low temperature, is proportional to T. Here's a proportional to T because of this. Then at high temperature, phonon scattering, so the vibration takes over, so there's something else at high temperature. So that's the typical results for the metal. Okay. So again, what I'm just trying to demonstrate today is that everything comes from the band diagram, effective mass here. You need to know effective mass. Once you know effective mass, then you can even think about thermal conductivity by electrons. You need to know concentration of the electron. Again, that is by temperature and band diagram. So that's that's why we went through the band diagram. I guess I move on to 2 or 3 more pages to complete the metal part. We finished the metal part today. Okay, I will also try to cover briefly the magnetic properties. To cover this in detail requires so many more courses. And there are other courses that teach magnetic properties. So I would just give you how density states density states play an important role in magnetic properties. Magnetic properties. First, let me define Bohr magnetron, which is given by mu b equals to q h bar 2m star. Then electron plays in the field B naught has a potential energy mu b naught. Okay? So even when B naught is as large as 10 Tesla, 10 Tesla is a huge magnetic field. 10 Tesla, we get mu naught B naught approximately 6 times 10 to the minus 4 electron volts. And what I just wanted to say is that this is a very small compared to, remember, Fermi energy of aluminum is about 11 electron volts. So Fermi energy is 11 electron volts. has an order of 10 electron volts. And even if you apply large magnetic field of 10 Tesla, electron can actually change potential energy by only 6 times 10 to the minus 4. So that's a very small energy. But that can actually induce some magnetization. So we define magnetization. Magnetization. M is given by mu B up minus down, then you get GE minus EF minus okay. So what I'm doing here is that is the following. Basically, I think about energy and I think about density of states, but this is a density of states for up, and here's the density of states for down. So what you get is the following. Without magnetic field is the same, right? But with magnetic field, for example, with the magnetic field in this direction, then you get something like this, which is so this is up and this is down. So of course, if the magnetic field is this way, this is favorable conditions. So energy becomes like this. Like this, something like this. Density of states. Okay? And here, basically the difference here is something of the order of EF plus mu B B naught. Okay? Sorry, this is not precise. I have to make it more precise. Originally, let's try to make it more precise. Sorry. Let's say this is a Fermi level. Fermi level. Then I want to move this one up and the other down. So it has to go something like this. That's okay. That's okay. But then we just need to have this is plus. So you have to have certain point, and this difference corresponds to 2 mu B B, right? Makes sense. Yeah. So that's the difference. And then there's only one Fermi level. Okay? So because of that, you have more upspin electron than downspin electron. So this induces magnetization of the material in this particular way, because we have more upspin electrons than the low spin electrons. Okay? So this equation becomes 0 EF plus minus mu B V naught is G E D E is approximately 0 EF G E D E plus minus mu B V naught G E F. So here what I'm doing is that because this part is very small, I'm just doing the Taylor expansion. Okay? Okay? And therefore, M simply becomes, if you take this into here, then M simply becomes mu B square G E F B naught. And magnetic susceptibility chi is given by mu naught M B naught, which is given by mu naught mu B square G E F. Here's this is a permittivity of the free space. So all I wanted to say here is that you see even the magnetization depends simply on the density of states. So that's why when people study magnetic materials, they always try to look for density of states at the Fermi level. Here's the density of the states at the Fermi level. So the density of states at the Fermi level is very important parameter for finding, okay, I apply magnetic field to something. Then how much is this magnetized while magnetic field is on? Depends on density of states at the Fermi level. Okay? Yeah. And I will not cover antiferro magnets and so on because that's quite involved. So last thing, so this is just a simple case where the magnetization is proportional to magnetic field applied to the material. So finally, I just give you two cartoons to complete the metal part, which is the Seebeck effect. I just, I have no equations to show. And Seebeck effect is something. I just want to give you the description of what it is. Here's one metal. Here's other kind of metal. And that is connected to voltage source. Okay? And there's temperature. Here's temperature T1. Here's temperature T2. This is metal A, and this is metal B. There's a similar case. There's a similar case where you actually put battery instead of the voltage source. You put a battery, and you by putting battery, you induce temperature difference. So now, here's the voltage. The difference between left and right is that left-hand side, there is temperature difference between T1 and T2, and because of that, the voltage applies here. Voltage difference appears here. In this case, you put battery. Just by putting battery, you actually induce temperature difference between position here and here. Okay, this is so-called Peltier effect, and this is Seebeck effect. And in this case, electric field induced by change in T is given by something like this, different kappa, and voltage is given by electric field. Voltage is given by dt. So how much voltage you can get is the difference between temperature 1 and temperature 2, and then you have difference in a Seebeck coefficient A and B. So I guess I can move on forever, but I just give you more intuitive description of what's going on. You see, we have two different metals. And if the temperature here and here is different, you can see the specific heat of this and this is different. So maybe for given temperature, electron on one side has more energy than the electrons on the other side, because of the difference in specific heat. And they have to distribute themselves by diffusion. So electron diffusion means, electric current. And that's how you get voltage here. In other words, if you apply certain voltage here, then you can induce temperature difference. And people use, there's a Peltier refrigerator. So that means one side becomes so cold, while the other side, I wouldn't say hot, but what is really creating is a temperature difference between one point and the other point. The other point is becoming so cold. Okay? And that is proportional to how much voltage you apply, because voltage and dt. So then again, that depends on the density of states. So that's it for the metal part.